In chemistry, this is a number you're going to be working with again and again and again. It's called Avogadro's number. If you haven't seen it, this video will help explain some of the details on how to work with it. So hopefully this DeBacco University video helps you understand Avogadro's number because it's something you're going to be involved with many different calculations. Now, when we work with Avogadro's number, it's going to be typically in the scientific notation, because if you were to write it out, this is essentially what it would have to look like. Many zeros after that. In fact, 23 zeros. So this is why it's important also to understand scientific notation. Well, let's get into Avogadro's number here, and it's a fundamental constant in chemistry that represents the number of particles, could be atoms, molecules, ions, other entities, in 1 mole of a substance defined as exactly 6.02, that's what we'll typically use, times 10 to the 23rd particles per mole. You can see it does go several other decimal places. Typically 6.022 typically is what would be used in calculations. This serves as a bridge between the microscopic scale of atoms and the macroscopic scale of measurable quantities like grams. 1 mole of carbon-12 atoms contains 6.022 times 10 to the 23rd carbon-12 atoms. So when you kind of think about this 1 mole representing this number of particles, this Avogadro's number, it became initially a little confusing, but as you work with it a little bit more and more, it definitely is a time saver. Now this Avogadro's number, this mole concept, think of it as a chemist's dozen. Think of it as if there's 12 particles per dozen. That's a simple conversion factor. If I have a dozen particles, well, I know I've got 12. Well, the same thing can be applied here. If I have 1 mole of particles, I've got 6.02 times 10 to the 23rd particles. So if we think about it in that regards, we actually use this very similar system, just with much simpler numbers. The mole is the SI unit for the number of substance, defining the amount containing Avogadro's number of particles. So when we look at kind of a visual comparison, here's zinc and carbon and magnesium and copper. All of these represent 1 mole. All of these represent the same number of particles, but we can see the masses are very different. You can also look here in the beakers, the amount of quantities of each, very different. Same number of molecules, but when an atom is denser or heavier, it's going to weigh more because we have the same number of particles. Just if we had a dozen ping pong balls or a dozen billiard balls, the billiard balls are going to weigh more, the ping pong balls are going to weigh less, but we still have that same 12 or dozen. Same concept here. We have the same number of particles because each one does weigh a little differently, a little heavier in some cases for zinc compared to carbon. That's why a mole of them, or a chemist's dozen of them, weighs more. We see that also with the volume. Now this gets into the concept here of molar mass, which the molar mass connection is Avogadro's number links an element's atomic mass, in atomic mass units or AMUs, to its molar mass in grams per mole. Conversions from molecules to mass require calculating the number of moles to make the conversion complete. Think of this as a simple unit conversion. While it may look a little confusing here, when you work with it a little bit more, it's a very repeated sequence of steps. So for example, carbon-12 has an atomic mass of 12 AMU, so 1 mole of carbon-12 has a mass of 12 grams, and that means it also contains 6.022 times 10 to the 23rd atoms. I try to give a little summary table down here that for trying to do conversions from the number of atoms or molecules all the way to the mass of a substance, we take the number of atoms or molecules, divide by Avogadro's constant to get to moles, take moles, and then we multiply by the molar mass to get the mass of the substance. We're going to work with some examples here, but if you kind of notice, whether we want to go from one end to the other, in the center portion is this concept of moles. So a lot of time you're converting to or from the number of moles to get to the proper unit you deem desirable or you're trying to calculate for. Other uses in chemistry, so this is not just a one-use thing. You're going to be very familiar with utilizing this number and working with it quite a bit. For chemical calculations, it enables stoichiometry, which we'll spend a whole unit on, allowing chemists to calculate the number of particles, masses, or volumes in chemical reactions. Looking at oxygen and hydrogen coming together to form water, we can see how the reactions and the ratios of these interact. With gas laws, 1 mole of an ideal gas at standard temperature and pressure occupies 22.4 liters, thanks to Avogadro's numbers, ensuring equal particle counts per mole. Again, it's offering this consistency. We see that here with this other conversion table or visual representation. All roads basically lead to and from the mole, or that Avogadro's number, or that Chemist dozen. And lastly, it's used to calculate molarity, which is moles per liter in solutions, relating particle number to measurable quantities. So this is something, it's a very large number, might seem a little scary at first. Working with it more and more, you'll see how it's integrated in many different aspects of chemistry.